All right, I'm going to begin. Good evening and welcome to tonight's STEMFest Cafe. Excuse me. The Secret Lives of Rare Elements, Finding Critical Materials for Green Energy with Dr. Mark Frank, Professor in the Department of Geology and Environmental Geosciences at Northern Illinois University. Our STEMFest Cafe is part of our month-long celebration of STEMFest and is brought to you by NIU STEAM in the Center for P20 Engagement at Northern Illinois University. I'm Dr. Judy Diamond, organizer of the STEM Cafes for the past 8 years and your host for this evening. NIU STEAM refers to science, technology, engineering, math, and the arts. STEM Cafes are fun, casual gatherings where adults can eat, drink, and chat with STEM professionals about hot topics and the latest research. We usually hold our STEM Cafes in restaurants monthly and look forward to getting back to those restaurants. Tonight, you will need to provide your own drinks, snacks, and favorite carryouts. In the meantime, one of our partner restaurants, Fatty's Pub and Grill in DeKalb, is offering a 10% discount to anyone who says they attended our virtual STEM Cafe. This STEMFest Cafe is part of our month-long celebration of STEM. Before I introduce Dr. Frank, I would like to share information about tonight's event. This is a STEMFest Cafe as part of NIU STEAM's annual celebration of all things STEM. Due to the coronavirus, we are celebrating STEMFest the entire month of October. Weekly, we will have at least 3 virtual events. We start the week with Maker Mondays for students and educators. We are holding STEMFest Cafes every Wednesday. And we are offering a STEMFest workshop each Saturday during the month of October. A limited number of people can attend and register to attend live, but we also have opportunities for people to attend virtually. And you can register for those events online by putting in STEMFest, and you will come to the different offerings that we will have during the month. We actually have the full schedule online, so you can search for STEMFest on NIU's website and you will come up with the entire schedule of events for the month. Connect with us on social media to get updates about STEMFest, but also about our ongoing offerings. We are gearing up right now for STEAM Studio, our after-school program, which will begin in November. We also are starting up Teen STEM Cafes in DeKalb in partnership with the DeKalb Public Library. Please share my contact information with anyone you know is interested. Encourage middle and high school youth to reach out to me or to the public library to find out how they can be involved in our Teen STEM Cafes. We really are looking for student leaders. You can get your limited edition of STEMFest 2020 t-shirt at oltstore.com. We have a lot of people that love collecting these STEMFest t-shirts every year, so we do have one for 2020. We encourage you to complete a STEMFest evaluation. You can find it on our website under STEMFest 2020 Eval. Tell us what you think about our month of STEMFest. I want to thank our sponsors for supporting STEMFest. We could not have this free family community event without their support. Thank you to Ideal Industries, ComEd, 3M, Nicor Gas, Thermo Fisher, First National Bank, and the Mortenson Company. So let's begin. Tonight's virtual STEMFest Cafe is The Secret Lives of Rare Elements, Finding Critical Materials for Green Energy. This cafe will be recorded and it will be posted on our website about a week to 2 weeks later, because we have to make sure that we have it closed captioned so it's accessible to all. For those of you that have not attended our STEM cafes before, our format tonight is as follows. Our speaker will talk for approximately an hour. During the talk and following the talk, you will be able to put in comments and questions, and depending on the comment, if it's needing to be answered right away, our speaker can see the comment or question and could actually answer it right then. The purpose of our STEM cafes is to engage the audience in discussion around a topic. So we know there are many experts always in our audience, and so we welcome those attendees and anyone else to add to the discussion. We will be ending by 8 p.m. If you experience difficulty hearing during the presentation, you can find a volume control, I think I mentioned this already, but in the upper left-hand corner of your screen that can be adjusted to your particular liking. Our speaker tonight is Dr. Mark Frank. Dr. Frank is an NIU professor in the Department of Geology and Environmental Sciences. He teaches courses in mineralogy, geochemistry, economic geology, and petrology. He conducts research in planetary geology and metallic ore deposits. His latest research focuses on critical materials for transition to low-carbon energy sources. Dr. Frank has a bachelor's degree from the State University of New York College at Fredonia in geochemistry. He earned his master's degree and his doctorate degree in geology at the University of Maryland. He was a postdoctoral fellow at the Geophysical Laboratory at Carnegie Institution of Washington. Tonight, Dr. Frank will be talking about whether we have the critical materials needed to support a shift to green energy sources. He will discuss the critical elements we need to acquire in a timely manner to support our modern world. The items we take for granted every day are made from materials that exist in incredibly small proportions within the earth. Dr. Frank, would you like to begin?
Sure, thank you. So everyone can hear me okay, I hope. The focus of the talk today, it's going to kind of go through a couple of sequences. One of them is going to be just talking about the materials that we're using, how that's working, the elements that we really need to make a transition to green energy, but also just for everyday life. There'll be some geology, sciencey parts in the middle, and then we'll come back to the bigger question, which is about the use of these for critical materials. So this is really the start of the talk, is trying to relate what we have here, which is this is a mineral, and here that is actually mined to obtain rare earth elements that we then need to be able to make solar panels and to be able to make wind turbines. So wind turbines and solar panels can't work without finding this mineral. And so that's kind of the basis of what this talk is going to focus on. So just the basic fact to start with is that right now we've been burning fossil fuels, which are essentially hydrocarbons. That process of burning oxidizes the carbon, and that process produces CO2. Now CO2 is a greenhouse gas that's going to actually trap heat in the atmosphere. And we can see the sort of relationship when we look at, and again, thousands of years, we see the amount of CO2 is drastically increased up to 400 parts per million in the atmosphere because we've been burning fossil fuels. Now, there obviously is natural variation we see coming back in time, but the deviation from that natural variation is very high over the last 1,000 years. That corresponds to a drastic increase in surface temperature as well. So it's a pretty well-known fact, and this is not something we can really discuss, is ultimately, what I mean by not discuss is that this is well-known, this is accepted, that as CO2 goes up, the amount of heat trapped in the atmosphere is going to go up. So that's initiating climate change, which of course we can deal with to some extent, but when we start melting glaciers, when we raise sea levels, all those things start to add up, and it makes it difficult for us to continue to have a normal society. So the solutions to these, as you know, most of us are solution-based people, are to either stop using energy completely. That is not a great thing, because I don't think society is going to go back to not having phones and not having electricity. Another option is to continue doing what we're doing now, continue to burn coal, continue to burn natural gas, but just deal with the effects of climate change and just say, okay, well, some areas are going to be inundated as oceans rise, and we just have to live with it, and we have to move cities. Again, that's still a difficult thing to do. Another thing, the last one, is to just ultimately switch to non-CO2 generating fuels. This would be nuclear power, wind, or solar. Right now, though, the United States uses about 80% of our energy is generated from fossil fuels. So even though we've made great strides in the amount of nuclear, wind, and solar that we're currently using, it's still relatively small when compared to fossil fuels in totality. So this shift, if we want to really mitigate the effects of climate change, we really have to do that relatively quickly. And so this talk is going to focus on what do we need to shift to non-CO2 generating sources, right? Non-fossil fuels. And even if you want to be on the side and challenge the effects of climate change, we can acknowledge that there are only so many fossil fuels contained in the crust of the earth and that are accessible. And so what that means is that all by shifting to wind, solar, or nuclear, all we're doing is shifting the energy sources that we utilize. In the past, at one point, we actually would hunt whales to be able to utilize their blubber to be able to make lamps. So this is one of the ways that we've shifted from that into burning coal, and this is just essentially another energy shift that doesn't necessarily require drastic changes in the fact of a year or two. The faster we make the change, the better, but this is going to take some time, as I'll talk about today. So for those that aren't into the science part, I'm going to just basically review the elements that I'm referring to and talking about. So this is the periodic table of the elements, list of all of the ones that are known to be in nature. The number 1 is hydrogen. That's because hydrogen has 1 proton. That's its atomic number. And as we increase the number of protons, we go from hydrogen to helium to lithium. That's represented here. The U.S. government has put out multiple reports, and the U.S. Congress is very concerned because there are minerals and metals that are critical to the economic and national security of the United States. So some of the minerals and elements we'll talk about today are focused on green energy, but a lot of the rare earth elements, which are depicted down here, it's in this part of the periodic table, it's actually in here but then expanded out to here, right? Those rare earth elements are actually critical in things like fighter planes, nuclear submarines, things like night vision goggles, and then even on the other side, another element that is considered critical for smartphones is this one over here, which is indium. Indium is required to make touchscreens. So it's an indium oxide. So without indium, right, we actually can't have touchscreens. You can't have touchscreen phones or tablets or any of that sort of stuff. So what we're going to focus on today, though, is more the energy side. And most of the energy ones that we care about are going to be here: iron, cobalt, nickel, copper, zinc, silver, gold. Those are all important. Molybdenum as well. And then select elements through this rare earth element area. So when you hear me say rare earth elements, I'm referring to these. These are not considered rare earth elements, but they're still in very, very small concentrations, and in some cases smaller concentrations than the rare earth elements, and are needed for society to function. So what do we use these things for? Well, I've just picked out basic ones. I didn't put all the elements and all the minerals that are required for these to function, just the ones that would be the focus of today's talk. So if we want to have solar panels, we need rare earth elements. We need copper, gallium, iron, indium, molybdenum, right? If we have windmills or wind turbines, we need rare earth elements: copper, cobalt, iron, molybdenum, zinc. For CFL and LED, this one's actually specifically an LED light bulb. That's a light emitting diode. Rare earth elements: copper, nickel, iron, manganese, tungsten. All those elements are required. And if you're going to buy the new iPhone, which is coming out soon, rare earth elements: copper, nickel, iron, manganese, tungsten. So I'm going to focus today on the things that we need for energy, but all of these minerals, all of these elements, all of these metals that we're going to talk about have applications for everything from your stove to your microwave to your phone. So these are the things that really allow society to function and allow for us to have these sort of things. So one of the questions put up here is, where are batteries on this list? And I'm going to get that in a second. Batteries are really important because these power sources, solar and wind especially, these are more for daytime. And so obviously for solar, that is predominantly energy generated during the daytime. So if you want to be able to use energy from the solar panels, you can only use it in daytime unless you store it in a very, very large battery, and then you dispense the charge that way afterwards. And so for those batteries, they happen to require rare earth elements, nickel, lithium, cobalt, nickel, all these different metals as well. So batteries tie into these top two here for the solar and the wind, because those sort of things, right, those can't generate power continually like a coal burning power plant or a nuclear plant can. Okay, so these are the rare earth elements, a list of the rare earth elements, right? And this is taken from a report to Congress about 3 years ago, and it just lists them coming down through here, all the different ones. And I know this isn't necessarily easy to see, but this lists all the different uses for those elements. So one of the big things out there that is very exciting are Tesla cars. They're beautiful cars. They've got a lot of technology, right? They don't utilize gasoline. It's completely battery cars. Right, so those are part of a classification of what's called electric vehicles, or EVs, which are denoted here, right, EVs. So one of the things that those need is you need to be able to make very strong permanent magnets. So this shifted down a little bit here from where it was before, but it's really neodymium is one of them here, and dysprosium, which is another rare earth element here. You could not make those batteries, right, so dysprosium here and neodymium here, you can't make these batteries without having these elements. So to make a Tesla, you need these elements in your material to do it. So in this case, people have calculated that if we do switch to wind and solar, if we move away from gasoline-powered engines, then we're going to need to increase the production, or how much of these materials, neodymium and dysprosium, by a factor of about 45 times over the next 40 years to be able to meet the demand for batteries in cars. So these are rare earth elements, and there's not a tremendous amount known about them, but they are critical for us when we want to switch to green energy sources. Okay, so just some historical perspective on mining and kind of how this works. Gold has been around forever. That's because it predominantly forms as a native metal. That's usually how we find it. It's been mined and known about since 6,000 years before the Common Era. So that's what BCE means, before the Common Era. Copper as well, silver, lead. The Tin Man here, that's at 1750 before the Common Era. Iron down here. Mercury, amusingly, is actually a liquid in most cases at the surface of the Earth, and so we don't usually, when it's pure mercury, we can find it in mercury minerals, but it can be found as a pure liquid. There's actually a location in Spain where you actually, in the rocks themselves, you can actually hit it with a hammer and liquid mercury will actually shoot out of it. It's really quite amazing. So the reason I wanted to show all of these is that rare earth elements, which are depicted here as these powders because they're refined into oxides, really we didn't know about them, and that's because we didn't find big deposits of them. We didn't find lots of issues with regard to where we could actually find minerals that held these, because they're at such low concentrations in most of the minerals we observed, and we didn't know what they were really good for. So we didn't really start to process them until 1880 in the Common Era. So all these other ones, maybe like gold, is roughly 8,000 years prior to rare earth elements. So because of the fact that they've only been recently explored, we don't know that much about them, about where they're found, how they form, and so we've been learning that over the time frame. So why is this important? Why do we care about the minerals? Why do we care about the metals? Well, to have society function, we need to be able to produce things that can allow for things like electricity. So every time you plug an outlet plug in something to an outlet, you get electricity from that, essentially electrons flowing through the copper. But to get the electrons there, to get the electricity to your house, you need infrastructure. In this case, we have steel towers with electric lines attached to them. So those electric lines, they're transmitting electricity, but we need the steel towers to be able to hold those up. So combining the steel that we need to make this switch into green energy, we've noted that since 1960, we've seen a tremendous increase in the amount of iron that has to be taken from the earth and has to be produced into steel to be able to make the infrastructure that we need to transmit electricity, to build cars, to build buildings, and that sort of stuff. So that's just iron in and of itself. So coming back to this is copper. This is the increase in copper since 1960, so everything's tied back to that. So copper, we don't use to make steel towers or anything like that, large towers. What we use copper for is in wire inside of copper for, let's say, coaxial cables, or inside of wiring in your house. That's because it transmits electrons exceptionally well, so that's what we can use it for. We need copper for solar panels. We need copper for wind turbines, not just for the turbines and the solar panels, but also to be able to transmit the energy that they produce. And so because of that, and because of the increase in population, we've seen this increase in the amount of copper production since 1960. So again, about a factor of 350% increase over the last 50 years or so, right? Rare earth elements have seen a tremendous increase. So we're now looking at an increase in the amount of production of rare earth elements that is 6,000% over the last 50 years. And that's largely because we need rare earth elements, right? You need those to make wind turbines. You need those in most new technology today, like things like cell phones, and more importantly for our discussion of green energy, if we want to switch away from using gasoline-powered engines and we want to switch to electric vehicles, then we need those. Without those, we can't make things like the infrastructure for the car, the battery, or the engine components. So these things are widespread, even though we don't talk about them a lot, and I've only talked about two so far. The rare earth elements themselves are not tremendously widespread, but they're used a lot. And that's mainly because for the production of rare earth elements, we've kind of taken them from mines where we're getting other metals, and we just kind of use these as a byproduct. But now we're actually exploring specifically for rare earth elements because they become so important in society. Okay? Okay, so there's a question in the chat just asking if I'm going to talk about the geopolitical and security risks associated with these, and I am in a couple of slides, so I'll get there. So it's a good question. Another question was, are the elements easily used and recycled? And in general, the rare earth elements are actually pretty easy. They are being recycled, but we're ended up using more of them. We have to produce more because the recycling is not keeping up with the demand. So this is production in addition to recycling. So we've increased production of rare earth elements by 6,000% to meet the needs of society, even while we've been going through recycling. And one of the things that I'll touch on, and I'll go back one slide, for solar panels and wind turbines, they have a finite life. So if we make them and we put rare earth elements in them, they have a lifespan of about 20 to 30 years. That's at least the current lifespan for these, until they have to be cycled out and replaced. So the rare earth elements we're using today to make solar panels, to make wind turbines, to make electric vehicles, we can recycle those, but that's going to cost money, and that's gonna the things that were in those cars today we can't use for new cars until those cars are off the road. So this goes to the question posed by Neil. This is looking at how rare earth element production has changed since we go back to about the 1960s. Right? Back then, other countries were dominant, but then the United States was the dominant source up until the 90s of rare earth elements. Right, so you can see that the U.S. predominantly at the Mountain Pass mine in California, which I'll talk about more in a second. This is what's been happening. But right around the mid 90s, we saw an explosion in the use of the rare earth elements and what was needed. right? So the US was providing, but so was predominantly China. And then what happened in the late 90s is essentially China undercut the market. So China drastically reduced the cost of at which they were selling their rare earth elements. That drove almost every other mine in the world out of production for a period of time. You can see that right here in sort of the early to mid 2000s. That's what happened here. And so once then China essentially cornered the market in rare earth elements, then they raised the price, and then now we have mines coming back online as we get to current today. So this process in the production, right now we are almost completely dependent on rare earth elements coming from China. And as I'll talk about in a second, the majority of rare earth elements that are mined, even if they're not mined in China today, are still sent to China, the actual raw ore, to be processed in China because they have such a large infrastructure set up to do this. Okay. So to talk about just how uncommon these elements we've depicted are, and the ones I'm going to discuss today, I wanted to sort of reference back to a very simple pie chart, right? All I did was take the elements that are most abundant in the continental crust, and that's because those are the areas of the crust that we actually can mine. We don't usually mine the ocean very much. We're mining the continental crust. That's where we're getting the elements we need for society. Well, oxygen, silicon are the two most dominant. Then you have aluminum, iron, calcium coming down, and then ultimately sodium down here, magnesium, potassium, titanium actually surprisingly is fairly abundant. But then right here, this 0.035 weight percent, that's all of the critical metals together combined. So there's a vanishingly small amount of these dispensed throughout the entire continental crust. So this little sliver here in the pie chart, that is the mass of all critical minerals that exist in the crust of the earth that we have access to. So when we look for these and we have to utilize them for society, we have to find areas that just naturally, by nature, have incredibly high concentrations of these comparative to the rest of the crust. So you need a concentration factor on the order of about 100 to 1,000 to be able to get to the levels needed for the mine to be profitable. So, all right, I'm not going to test people on the mineral formulas, so we're not going to go crazy about this, but I wanted to put these in here because in nature, we don't usually find these metals in their native form, right? And that's important because when we try to look for where they could be, we don't look for places that are just, let's say, cobalt or nickel. We look for the minerals that cobalt and nickel would be found in. So I put up a fair number of minerals here, not all by any means, there's 5,000 minerals, but I just put a couple. Gold is found as a native metal, right? That's one of the few. Copper, you can find metallic native copper. It does exist, but in ore deposits, it's not that common. There's a bunch in the Upper Peninsula of Michigan, but by and large today, we get our copper from things like chalcopyrite and bornite, which are sulfide minerals. And you'll see that nickel, most of our nickel is going to come from a mineral called pentlandite, which is a sulfur-bearing mineral. Most of our lead comes from galena, which is a sulfur-bearing mineral. Most of our zinc comes from the mineral sphalerite, which is a sulfur-bearing mineral. And you can see the nice images of what those minerals will look like. And by the way, those of you from the state of Illinois, galena, there's actually galena in Galena, Illinois, right? There actually are deposits of galena and sphalerite, and that's one of the reasons people relocated to that area, at least some of the original settlers, because they were mining those metals. Cobalt exists as a sulfide as well. So what I want you to take from this slide is not the mineral formulas themselves, but there are some minerals that will group together because they're all tied and bound with sulfur. So in this case, we're going to look for where there's high concentrations of sulfur to find these elements. For elements like iron, we find those with oxygen, like hematite and magnetite are the minerals. So those are not going to be found in the same locations as we find these high sulfur content minerals and metals. So those are kind of the basic ones, the copper, the nickel, the lead, zinc, those types of things that we can have. Now, rare earth elements are in really unique minerals that almost, I would guarantee the majority of you have not heard. So this is rare earth elements here, right? This is bastnäsite. This is a rare earth element. So when we type rare, REE, that means rare earth elements. That was on that periodic table, that lower level one, right? So that is, when they form, they just form with an amalgamation of these. It's not just one rare earth element. There's usually a bunch in there. They're all going into that mineral. So the thing I want you to take from this is the top three are associated with CO3. That means they're carbonates, just like calcite, dolomite would be carbonates as well. So those are carbonates. These other ones, monzonite, xenotime, apatite, those are phosphates, PO4, PO4, and PO4. So from these two slides, and I'm going to go back one slide to this one, we have predominantly sulfur-bearing minerals that happen to have metals. We have oxygen minerals with metals. Over here, we have, in rare earth elements, two subsets, right? CO3-bearing minerals and phosphorus-bearing minerals. So you can see on these two slides, it's showing you a range of metals that are important for critical metals and critical minerals, and for us switching to a carbon-free energy system. But they're all a little different, and that will actually inform where we're going to actually find them. Okay? So, this is where we'll get into a little bit of geology, and so if you're not into geology, it's okay. There'll just be a couple of slides on these, and then we'll go back kind of the grand scheme stuff. So this is essentially a map of the world, and what I wanted to show here, and it kind of got cut, so we're going to do this kind of backwards. This here, right, this string of volcanoes exists, right? This is where we actually have porphyry deposits of essentially copper, plus or minus gold, plus or minus molybdenum, right? And so all along the South America, the west side of South America, the western part of the United States, up into Alaska, we see those as well over here on sort of the far east. All right, we have some in Japan, we have some in Australia, we have a bunch in Indonesia as well coming up through here. So around the Pacific Ocean, we find a high number of copper, gold, molybdenum, and some REE deposits. And that correlates with what is known as the Ring of Fire, right? That's this depicted here. That's Ring of Fire. And so we call it the Ring of Fire in geology because we're really referring to this being a string of volcanoes that exists circling the Pacific Ocean. So if we note that their correlation between the string of volcanoes and the metals that we see in those same locations coming here and then on this side over here on the far east, we can suggest that there's a correlation between volcanoes and some of these critical metals. Not all, but for some of these critical metals. So it appears that volcanoes, which are molten rock, can help to form these types of deposits that have these metals we need for the shift to green energy. Rare earth elements are more complicated. There is some overlap, like on the western U.S. here. This is the Mountain Pass mine in California, right? We have some up here in Alaska. This is a specific Vulcan deposit that's being explored right now that's associated with it, right? Some parts of the western U.S. here. But then we get into the central U.S. in these domains here, and in the eastern U.S., where we don't have active volcanic activity, but we do have potential for rare earth element deposits. So the other thing to take from the slide is places that actually have rare earth element here, rare earth element production. We have Mountain Pass, we have some in India, but we have the largest number in China, a couple in Russia, but China really has cornered the market on rare earth element production. Okay. So now what we're going to do is we're just very quickly going to do kind of a Geology 100 level discussion of where we're going to see molten rock form. So this is a 100% Geology 100, very simplistic cutaway, but what it shows is where we have oceanic crust here, the continents here, so this is what we live on, right? And this is what's below the oceans in this zone, right? In the middle of the Atlantic Ocean, there is one of these things called a mid-ocean ridge. This is where the tectonic plate for the ocean is moving away from each other, one direction here and the other moving the opposite direction. And so the Atlantic Ocean is actually getting bigger every year because of this expansion. right? So we're actually making new crust here at what's called a divergent spreading center because we're diverging the crust apart and we're spreading it apart there. We can actually have where that crust that's expanding and moving across eventually can hit the continents. When it does so, it subducts below because it's more dense, right? And then we can actually generate melt here or magma that then rises up and at the surface of the continents makes a volcano. So volcanoes are either going to be made through subduction zone processes, undersea volcanoes in a rift zone like is here, or divergent spreading zone. You can also get them at mantle plume zones. This is like what we see at Hawaii and Yellowstone. And then you can actually have oceanic crust subduct below oceanic crust, like we would have in the Far East. That generates molten material that then rises up. So I went through this because it does appear that a lot of the metals that we care about are associated with molten rock. So that's where we really want to focus. Well, how does the molten rock form? And then how do the metals form associated with that? So divergent spreading center, the reason it happens is because the crust starts to spread apart from itself. So it cracks. This oceanic crust moves to the left as you look at it, and this part moves to the right. It makes an open space here that immediately fills with mantle material, so the mantle wells up. As it does so, it undergoes what's called decompression melting. All that means is that we have solid mantle, the mantle's solid. The mantle will flow up. Part of the mantle, a small amount, about 15%, will melt, right? It'll make a magma chamber. This is molten rock here. Some of the molten rock makes it to the surface, right? And then it forms oceanic crust. And that's how we actually make oceanic crust, is in this type of setting. Now, the critical rare earth elements that exist are coming up from the mantle. So there are rare earth elements, there are copper and gold in the mantle, and those things can come up and they can be enriched in these types of areas here. Now, I'm not going to spend a lot of time on that, and that's because we don't get a lot of the oceanic crust onto land. It does happen, but we don't get a lot of that. So a lot of the deposits we're going to see are going to be associated with continental crust. So this is how we make oceanic crust. This is where we can get some of these materials. Then what happens is that when the oceanic crust, as you see it's listed here, when it spreads out, eventually it's going to hit something else. If it hits a continent, the continent is less dense and will just kind of ride above, and the oceanic crust will actually subduct down below. As the oceanic crust subducts down below, it's taking with it all the metals that have been released from the mantle into that oceanic crust. So everything comes down. Now, when that happens and we get down to this zone, some of the material is released back, right? And that's because water comes down with the oceanic crust. And as that water is released back, it takes with it elements like copper, like gold, like molybdenum, like indium. A lot of the rare earth elements can come back up. So essentially, we increase the concentration of rare earth elements and of copper and gold from the mantle into the oceanic crust by that partial melting that we talked about at the mid-ocean ridge spreading centers. Then as it goes down, we actually increase the amount of metal even more in the fluid coming back up because the water is not taking every element, it's only taking some. And then those highly enriched elements are now pushed into the continental crust where they react with the continental crust. We get melting here, and so we end up with lower parts of the crust that are enriched in elements that came off of the subducting oceanic slab. Now, when I say enriched, I'm talking about an increase from maybe in the part to 1 to 10 part per million zone here. That means if I have a million pieces or a million atoms in the rock, maybe 1 to 5 to 10 are the metals we care about. Then we get up into here, we might be at 10 ppm. Then we go down the subducting slab, we might be able to increase those concentrations up into 100 ppm. So it's still not high enough for us to be able to utilize, but it's nature actually going actively through this process and increasing the concentrations of those metals until we get up to these shallow zones here. So when I use the term fertile source, I'm really just referring to our ability to increase the amount of metals in that system through natural processes. So the final stage for a lot of these is that we make a melt at depth in the crust. That melt is enriched in the metals relative to the original mantle. That melt can rise up into shallow parts of the crust that are accessible today. That melt is, over 650 degrees C. So think 700, 800, 900 degrees C. So it's the same stuff that would feed in and form a volcano. Most of the time, at the depths that these deposits are going to form, we're looking at pressures that are between 50 and 200 megapascals. That's somewhere between 7,000 and 30,000 pounds per square inch. So pretty high pressure. Now the magma that exists here, it has elements in it like silicon, aluminum, oxygen, potassium, sodium, but it's also got metals. It's got copper, gold, molybdenum. It's got the rare earth elements. What happens is as this magma solidifies into a rock like granite, the metals don't want to stay in the rock and the water doesn't stay in the rock. So when the water leaves, it takes the metals with it, and then they move to the areas around the magmatic body into this ore zone. This is called the porphyry ore zone. So it's the fluid combined with the metal composition that's fertile in the magma that allows for us to be able to produce metal deposits that are actually high enough concentrations to be able to utilize. Right? So that's one of the processes. So this is really just a picture of what can happen. This is granite. So a granite that is solidified had maybe 1 to 100 parts per million or micrograms per gram. So very low concentrations. But by the fluid, removing the metals from that area and moving them to a smaller volume of rock, we can get up to 40,000. So we can see an increase in concentration on a factor of 10 to 40,000. That's a substantial increase. So that's nature actually allowing us to concentrate, and it's concentrating the metals to a point where we can actually utilize those. So this is a large deposit. I put this here for a couple of reasons. One, to give you a feel for how big these can be. This is the Grasberg deposit. This is it. Its elevation is 14,000 feet or 4,300 meters. It's essentially the top of a mountain. So this building down here, this is one of the processing buildings here. You can see two of them. To give you a feel for the scale of this, that building is 3 football fields long. So this is a tremendously large deposit. And the amazing thing, it wasn't discovered till 1988. And that's important because it shows us that not all metal deposits are known, that we're finding some day after day after day, and we're exploring for them. And the reason we explore for them is because they're worth a lot of money. This one deposit, when it was formed, if we look at today's prices, has $170 billion of gold, $209 billion of copper, and just a paltry $8.17 billion of silver. So in this case, we find gold, copper, and silver, all metals that are important for batteries, for electric vehicles, for electricity generation in this one deposit that was found relatively recently. Unfortunately, rare earth elements we know a lot less about, and this goes back to the history of mining that I showed you. The issue really here is that gold we've known about for 8,000 years, and we've been looking for it, mining it, getting better ideas of where we can find it and where we can't find it. We really didn't even isolate the rare earth elements until the 1880s, so that's only been a little more than 100 years, so we're 130 years in, and so when we look at those, we have to take that into account for our exploration models. So in this case, that's why we're looking in a wide range of places, because we're still trying to understand. To give you a feel for how difficult this is Boken Mountain. This is actually in Alaska. This is where the rare earth elements are concentrated. You can see a hammer there for scale. It's not these big, large areas where we have just a whole big seam like we do of coal or of other rocks in the ground. They're small concentrations that are really difficult to find. And so it's taking a while for us to catch up to being able to explore for these rare earth elements. One of the things that we've learned, though, is that the same processes that will work for copper, gold, right, it doesn't matter in this case. Right? That alone is not enough. So the same magmatic hydrothermal system we just talked about for copper, gold, molybdenum, silver, like that formed Grasberg, those sort of things can increase the concentration of rare earth elements, but not enough. And we have to look for a specific type of granite, an A-type granite. That's a granite that has a high amount of potassium and sodium, right? Those are kind of rare relatively. But what does increase the metal concentration in rare earth elements is that once we have the granite form, as is depicted here, weathering, rainfall can come in, can take rare earth elements from this part and then concentrate them into this zone here. Some of the largest rare earth element deposits in the world formed because of weathering processes. Rainwater took metal concentrations that were sub-economic, that weren't that exciting, and increased them by a factor of 10, a factor of 20, to the point where they actually became economic, to the point where they're good deposits. So the U.S. is actually exploring for some of these. This one is actually in the mid-continent region of the U.S., right, of an older zone. This is near the Ozark Mountains, where we're actually looking for some of these types of deposits. There's another type of rock where we can find a lot of these. It's a really weird rock. It's called a carbonatite. It's a magma that is extremely rich in carbon and has lots of carbonate minerals in it. And so it's actually calcite, all these minerals that we normally think of in sedimentary regions, right? The Mountain Pass mine in California is one of these carbonatite deposits. So over the last 30 or 40 years, we learned a lot about where to look. So for these deposits, where groundwater is important, we're going to have phosphate minerals there. Remember, we talked about rare earth elements are either phosphates or carbonates. In these carbonatite type deposits, the minerals are carbonates. So we know if we're looking for, in a carbonatite, we're going to look for certain minerals that are carbonate-based minerals for the rare earth elements. Conversely, if we're in, let's say, a weathering zone, we're going to look for phosphates. Okay. So we are searching for these in the U.S. The Mountain Pass in California is the only mine in the U.S. that's operating today for rare earth elements. So all our electronic batteries, everything that requires rare earth elements, there's one site in the U.S. that is currently operating. And the Mountain Pass mine has gone through 3 or 4 changes of ownership in the last 15 years because people will open the mine, they'll start to get it to produce, but then they lose money, they shut it down, and then it moves to someone else. So we know that in this zone here, right there, that's a carbonatite deposit. We get up into Idaho zone, carbonatite, right? But when we start looking in mid-continent, and especially in the southern U.S., there's potential rare earth elements here because we're looking for the set weathering profiles. Okay, so that's through the geology part. Now that we have an idea that we know where these things can be found, we have to talk about the basic question. Do we have enough of these critical metals and critical minerals to implement green energy? The answer is yes, we do actually have enough in the crust of the earth. We just don't have enough that we can bring to market now. So if you said we want to switch over to green energy sources, wind and solar, today, could we do that? And could we just get rid of fossil fuels? The answer is no. All right, it's just a hard stop no. You can't do that because we just don't have enough of the metals to do it. Combining that with the fact that, as you see here, if we think about wind energy, right, these are offshore, this is onshore, the majority of source for those rare earth elements is coming from one country, which is China. So getting into trade wars with a country that controls the critical metals is not a great idea, right? So we want to avoid that type of stuff, because not every country has every commodity that they need to function. Now this graph here, what I wanted to show here is that this shows just roughly how much the metal production has to increase for all these different metals, depending upon whether we want to actually do nothing, which is depicted here. This is just normal. These first two are just normal increases as society is using more things. Right? If we want to be aggressive and we do want to start switching to green energy as fast as we can, then we are going to be needing increases of somewhere on the order of 10, 12, 15, 40, 50%, or 50 times, not 50%, 50 times the increase in production just to be able to keep up. We do have enough metals to do it. There are enough deposits, but we have to be able to mine those more effectively and more efficiently to do it. And so this goes to the question that Neil posed earlier, is like, are these sources, geopolitically stable? And again, I do the same thing where I give both answers. The answer is yes, we're doing it now, but no. And the reason I say that is if there is a trade war with a country like China that happens to contain the vast majority of the world's rare earth elements, then we're going to lose that rare earth element supply. It's just not going to be there. Conversely, another element that's critical for batteries and critical for green energy is cobalt. Cobalt is almost predominantly sourced, and we're talking about 90% of the cobalt in the world is coming from the Democratic Republic of the Congo, which, if you know much about that, it's not a tremendously stable area. So these areas where we're actually reliant on these very important critical materials, these critical metals, and again, we're not just talking about for green energy. We're talking about things like night vision goggles for military applications, for everyday applications we use, like for indium that we use in smartphones. Then we have many sources, but the best developed ones, the ones that we're currently utilizing, are here in countries that at a moment's notice could change in their attitude towards the U.S. and towards Western countries. So that's a big problem, and that's something that the U.S. government is actually trying to work towards and trying to fix. So this is the geopolitical situation. This is complicated. So the basic question now is, how do we find more of these things? What can we do? And it's not just now the geopolitical side. It's how do we get more of these things to be able to switch as the world to these green energy sources? Well, first is field studies. This is where geology begins. We go out, we look at rocks, we look at what they are, we characterize them, we know if they're phosphates or carbonates or if they're sulfides, and we use that to be able to inform where we could go next. The next way is we can use large range magnetic systems, geophysical systems, that allows us to be able to map out where things are below the surface, or at least under cover of trees. So this allows us to not just look at what's at the surface, like in the field studies, but we can actually look at things that are below the surface. That will give us another clue as to where we need to go. Once we find a potential location that could host these minerals, then what we do is we go to the surface, collect samples, and we can do chemical and mineralogic analyses. Do we have the minerals or the chemicals we need? Do we find neodymium or do we not? Once we do that, most of these are below the ground, so then we drill holes in the ground. These are some pictures of drill core. These ones are, I think these ones are from Nevada, so these are Carlin Trend drill cores looking for gold, right? So this is gold deposit. So that's what we do. We drill down, we know how deep to where we find the minerals and the metals of interest, how long or how big that deposit or that ore body is, and then we go from there as we move forward. Right, now what are we doing at NIU to try to help this? Well, the type of work I do, and you can see pictures of some of my students here, is that we do laboratory experiments to try to recreate what people have found in the field. We do microanalytical analyses of those different deposits. We take all that data and we make thermodynamic models and formation models that allow us to be able to tell the people looking for these critical metals, where do you go, what type of tectonic environment, what type of minerals should you look for, what sequence of minerals. So the work being done by myself, my grad students and undergrads in my lab, this is all what we're striving for, is to get better information as to where to look. Because if we know, at least to a greater extent, where to look, then we can do so more efficiently, which saves money, but also which helps to make deposits that are environmentally safe and sound. So will we succeed? So this is going back to a report by the Club of Rome. It's a book, The Limits to Growth, that was published in 1972. It suggested that we would run out of important critical resources like oil. If you go back to the 72 book, they suggested we would run out of oil in the 90s, which of course didn't happen. And that's because even though population has increased from 1 to 6 billion from 1830 to 2000, and we're at 7.8 billion currently, that generally the global use of a material has kept up with production. So you can see for copper, right, for gold, for bauxite, which contains aluminum, right, this is production here. We're seeing that, yeah, we're using more of all these commodities, as I showed you before, all the metals, but we're actually seeing an increase in the amount that's produced. So we're keeping pace. We're finding deposits, we're getting materials on the ground that are allowing us. So this is the optimistic side of things. So I can say that we've done this in the past. We've been able to move through and find more copper, find more gold, find more oil, find more bauxite, all that sort of stuff, and be able to improve technology to do so. So as an example here, this graph ends at 2000, and that's why I like using it. This is the world production in oil. It goes up. The USA, it comes up, and then it flatlines. This is where you heard terms like peak oil, like we got to the maximum amount of oil that we can produce. Well, now the U.S. is one of the world's leading producers of oil. We're way up here now because of new technology. So that new technology has allowed us to be able to produce oil and gas. So with that in mind, though, oil and gas aren't going to last forever. So the shift to green energy is something that we should still continually do. So I'm an optimist saying that I think we can find these resources. We just have to put the effort in. So I think we can minimize the impacts of climate change. We can do so by switching to things like nuclear power. We can switch to things like wind. We can switch to solar power. And I know there's issues with nuclear power. Right? There are also issues with the mining that's required for these green energy sources. There are negative impacts of mining. There's no way around that. That happens. But those are relatively small footprints and small comparative to the impacts that will occur through climate change. So those are far greater consequences. So ultimately, in my mind, one of the biggest issues we're going to have with meeting this green new energy is time. The time to find these new deposits, to find these metals. The time to characterize them, to be able to characterize the deposit and to approve a mine. Right now in the United States, we're looking at somewhere between 10 and 20 years to be able to find the deposit, once we find it, to even get it online. Other countries, Australia, Canada, are much, much faster than that. So even if we can find the deposits, we have to streamline the process to be able to bring those deposits online. That doesn't mean that we do so in an environmentally unsound way or in a way that will harm society, but we have to smooth that out and make that go faster if we want to switch to green energy sources. And so what I wanted to put in the last part of the slide is this is the amount of new materials that we need for solar, this is for hydro, this is for wind energy, geothermal, right, which I haven't talked about today, but we can in the question period, and this is for natural gas. Right? Natural gas produces CO2. It's a greenhouse gas. It's not nearly as bad as burning coal, so that's an advantage. Right? But this is natural gas, something we could use to be able to get to where we have enough material to do solar, wind, and switch completely to green energy. Okay, so I'll stop there. I'll try to answer some of the questions. One of the questions was about the historical problem of nuclear energy and the waste. That's exactly right. That's one issue. There are new reactors, technology out there that doesn't produce as much waste. There are ways to refine the waste, but you're absolutely right. The waste is a big problem for nuclear energy. The government had set up to do Yucca Mountain, but that's ended, so that's not going to happen. So that is a huge problem that has to be addressed if we're going to continue to use nuclear. So that's a problem. So if you have any other questions, I can get to those. We'll look at the back here. And so someone asks, what's special about the REEs? The best way I can describe it is if you've got a magnet that you need and you have a kitchen magnet, right? That's usually magnetite. It's usually iron-based. And those are strong. Those are good magnets. But for applications associated with like electric vehicles or for climate change, what we really need is we need super strong batteries, right, to do that. Otherwise, we can't do it. It just won't work. And so we need neodymium, which is one of those elements that makes those super strong magnets. So if you ever heard of the really strong rare earth element magnets or certain types of magnets, their properties are just different. And without those, we can't actually make batteries small enough to be able to function in electric vehicles. So I hope I answered that question. So I'm done with my presentation, so we can do questions. Judy can come back in, or however we want to continue with the discussion. Okay, so let me see if I can see some of the other questions here. Yeah, so Rich Lasson makes a good point. Aquila's, it's a gold zinc deposit. It was discovered in 1999 as a great example, and the mine is actually going to start construction in 2022. So that took 23 years from discovery to the point where we're actually being able to mine that deposit. So that lead-in time, that's one, I think, of the critical issues, is that I think we're going to be able to find the deposits that switch to green energy sources. It's really just going to be a question of, can we make that switch fast enough? Even if we find the deposit, it does take time for that material to come online. So Evan asked the question is, are the rare earth elements all interchangeable with each other? they will go into the same minerals, and so that's why we'll find things like carbonates and phosphates that contain a lot of these rare earth elements. But their use and what we use them for is highly dependent upon the actual element and its properties. So one of the slides I showed early on, we don't have to go back to it, one of the slides I showed early on would list the different things. So for example, we can use some things like germanium that will go into night vision goggles. Neodymium predominantly goes into batteries. Even though they may be found in the same mineral in the same deposit, we mine them, separate the metals, and then use them for different things. So Jennifer asked the question, is mining the oceanic crust possible? There's efforts in that area to do that. The challenge is that a lot of the metals in the oceanic crust are contained in sulfide minerals. And one of the byproducts of working with them is that you can actually make sulfuric acid. And so there are consequences to doing that of the ocean. There are oxide minerals on the ocean that we could mine with no problem, but the sulfide ones have given people pause because it's an ecosystem that is more difficult for us to separate, whereas for things on the crust and in the land, we can separate those, we can make barriers, things like that. Okay, so the next question, is there material science research seeking to find artificial development of REEs? There are synthetic diamonds, why not synthetic REEs? And that's a good point. So Robin makes a good point. For diamonds, and I've actually done some of this, we actually can grow diamonds in a lab. We can do that. And we're doing that where we're taking carbon, in that case, carbon that's in the form of graphite or some other form, and then we put it at high pressure and temperature. That's one way to do it. The other way is what we call through a plasma. It's a plasma growth. We can do it that way. But we're basically taking carbon and just changing its form to diamond. For rare earth elements, on the other hand, we just need that neodymium. And I know they're listed as rare earth elements, but actually gold is much, much lower concentrations than the rare earth elements are. So we do have enough. It's just about finding them and processing them. It's not something that, at least at this point, we can synthetically make. So Judy, is it okay if I just go through the questions, or how do you want to proceed?
No, that works. But I had a comment about one of the first questions about the nuclear waste. I know that Argonne is working on different methods of either recycling or using those materials, or what to do with nuclear waste. So, and I think we had not too long ago a STEM cafe on that. So we can be reassured that somebody's working on it anyway.
Yeah, and that's exactly right. All of these things, there are consequences. Mining, there are consequences to that. There are consequences to using nuclear energy. And to be honest with you, there are actually consequences to making solar panels. There's waste from that. There's waste from the wind turbines. There's just no way around that. It's really a matter of, you're sort of doing a cost-benefit analysis or a risk analysis. Which one is worse? And in this case, from the projections we see for what climate change can do to the globe, it's actually much better for society to increase mining and to shift to those green energy sources in the time frame that we can. That's really what we can do. Okay, so James asked, how do you differentiate the REEs from one another when refining the mined mineral? It's a good question. Some of them are magnetic, so you can actually, once you process the material, you can remove them with a magnet. So essentially you break the mineral down into its kind of common constituents and then just use a magnet to pull some of them out. Some of them are more dense than others, so you can use flotation or settling as well. There's a whole bunch of, and one of the slides I showed, I didn't show, it was at the end, it goes through that. There are ways to do that. That's where the material scientists and the engineers come in to figure out and to do that the best, and the chemists and the physicists. The geologists do that as well, but for what I typically focus on, I just focus on finding the ones that we're looking for. All right, so the next question from Rich is, can oxidized iron formation be a source of REEs? Generally, they're there. The rare earth elements are in those iron oxide formations, so they exist. And so there's a lot of these in the Upper Peninsula. The problem is that there isn't that much of it there, and you'd need to be able to take the REEs and concentrate them by weathering processes. And so you essentially need to flush them to a zone where they're concentrated. There are certain types of deposits with copper that happens, and that's a kind of a low temperature zone. But the iron oxides themselves generally don't have high enough concentrations of REE to do it, and the weathering processes can't affect the iron oxide enough to break it down to concentrate the REEs. So at this point, I don't know of any deposit or of any exploratory system that's looking at iron oxides, because I just don't think they find the REEs at high enough concentrations. Okay, so Greg asks, do you have any recommendation for people to help maximize the effectiveness of electronics recycling? Yeah, one of them is don't throw things in the garbage. And I say that kind of in a flippant manner, but it happens. A lot of people don't do the recycling and just throw things like batteries that have lithium in it that could be recycled, that have rare earth elements, and they just throw it in the garbage because it's easier to do than to recycle. And even in the city of DeKalb, the recycling requirements for some people are a bit onerous, and they won't do it. And so I think we've all seen TVs sitting on the side of the road where it's not easy to go drop them off, or in some cases you have to actually pay for them. So that's something that we could do in society to make that easier, to spread that information. We all have recycling bins, at least a lot of us do. We recycle plastics, we recycle cardboard, we recycle paper. If we had a more or an easier way to recycle those, I think that would help. How that would work, I think making drop-offs easier rather than charging people to recycle some of the electronics, as is currently the case in some localities, I think that would be a big step forward.
Can I say something?
Yeah, go ahead.
We are in April going to have a talk on trash talk. And we are also, Waste Management is going to join us just so they can talk about the recycling part, but we're going to be talking about reusing and retooling things. But I will ask them ahead of time to address some of these pickup types of things, and what's the answer to that.
Yeah, one of the, and again, this is kind of like dirty laundry in a way. One of the difficult things is that a lot of our electronics recycling we send over to less developed countries, unfortunately. And that's because the environmental regulations to recycle them in the US or Europe are so stringent and so expensive, it's not worth it to do it. So this is where I think we as society can actually make that jump and say, hey, you know what we're going to do? We're going to make this easier. We're going to make this easier for people. We're not going to charge as much because this is a critical thing we can do. But the price comes someplace. So you either have to raise taxes or you have to raise the cost of doing it. And typically we don't do it with taxes. We kind of shuttle it off to the companies to try to have to deal with it.
We really didn't give people a chance to refresh their drinks or anything. We just went into the questions and answers, which we can give them a few minutes to put some discussion items in here.
Yeah, that's great. Any questions, any comments, feel free to share them. I think I answered all the questions, so if I didn't get to your question, just write it again and I'll do that. I'll do an asteroid question. Actually, that'll be interesting. So which one is that? We get these materials from asteroids. That's a really good question. The answer is there are these elements, especially nickel, iron. Those ones are common in asteroids. There is talk about different countries going out in space exploration, grabbing a hold of these asteroids and then bringing them back to Earth. I don't know if that's what the dinosaurs tried to do when they killed themselves with one, so we have to be careful about how we did that. But that is a legitimate thing people have discussed. But really, then it's a cost thing, right? The amount for that space mission is far more expensive than going to California and utilizing the Mountain Pass mine. But I could definitely see, I never sleep on technology. It's always improving. Maybe that will be something that we could do in the future, definitely. But at this point, it's been talked about, it's been discussed, but it's not considered seriously, at least to the point where there's anything planned. so good reading materials. There's actually there's quite a bit online, and there's a really great report from the USGS, United States Geologic Survey. There's some really great information, some really nice written reports that are freely available. There are some good books as well. So I think the easy thing to do, and Robin submitted this question, if you want to submit that, send me an email. I can forward you the reports I have and give you some lists of books if you want to do that. I'll type my email in here. And so
Mark, I know that the library has done this for me before, that they will research some of these websites and other books and materials on this topic if we would like them to. It sounds like you already know some. And I think one of the questions was whether you would share your PowerPoint.
Yeah, that's no problem. Some of this stuff is mine, obviously. Some of this is just open source reports, so that shouldn't be a problem. Yeah, we can make it available to whoever wants it. That's not a problem. Yeah. Okay, so then Evan asked a question about geothermal a little bit. How do rare earth elements play in the geothermal, and how important do you think geothermal energy is compared to other sources? My master's work was really on geothermal energy, and geothermal is a really great source of electricity because it's always on. So the way geothermal works is you have hot rocks at depth in the earth, or even a magma chamber at depth, that heats up the local groundwater, and then you bring that groundwater up into essentially a heat exchanger, and then it heats up other water, which then turns turbines and generates electricity. That's kind of how it works. So the reason I went through that explanation is that for geothermal to work, you need water and you need hot rock. And unfortunately, in many of the places we actually have rocks hot at depth, we don't have water. And the places we have lots of water at depth, we don't have hot rocks. So geothermal is kind of restricted to some locations, like Iceland's a great example. It's perfect there. There's geothermal energy in California, especially near the Sierra Nevada mountains where they get enough snow melt to do it. But like geothermal energy in Utah and in Nevada, where there's not much water, the rocks are there, but the water isn't. So that doesn't work. Now, for the REE specifically, that energy source requires some REEs, but not nearly as much as what you have as you need for wind and solar. So if we went geothermal, we'd be more restricted geographically, but we wouldn't need as many of the rare earth elements. We would still use copper and stuff and iron for the systems, but not the rare earth elements per se. And so Mia asked, what got you into this field of study? For me, I'm not one of the geologists that loves minerals, and I mean, I love them and they're pretty, but I didn't do it for that reason. I just wanted to know how things worked. And for economic geology, or for this stuff that I do, and I do other things too with diamond anvil cells and high pressure work and planetary, but for this, one of the things that interests me is the processes require things like magmas, water. There's a high amount of chemistry in this. There's physics in this, so that's kind of all things I'm interested in. And it also has real applied things. And my parents didn't go to college, and so I was first generation in college. So I always had a very strong bond to, what am I doing and how does it relate to the real world? And this is one of the areas of geology that definitely relates to the real world. And so then Rich asks, do you think mining manganese nodules from the ocean bottom will sufficiently add to the RE inventory? So that's a really good question. So manganese can exist in minerals that form essentially in the ocean floor, and this is at the spreading centers, the divergent centers I talked about. There are some rare earth elements in there that, of course, would add to the inventory, but you would actually mine that for the manganese and probably some nickel, and there's some other stuff in there as well. And then the rare earth elements you would get would just be kind of, the icing on top of the cake, so to speak. It wouldn't be high enough concentrations to do it, but people have talked about mining those specifically for the manganese. Now, manganese is used on lots of different things as well, and these are either manganese sulfides or manganese oxides. So that is another source. It wouldn't be a primary source where we're going there looking just for the REEs, but we would get a different metal that would actually make it economic, and then get the REEs as sort of a secondary thing. All right. So then John asks, what about the distinction between economic exhaustion and physical exhaustion? While we continue to find new deposits, they get relatively more expensive as they become physically scarcer. How will this play into the direction we move in the future? And any thoughts on how China's attempt to capture ownership of rare earth materials? So a lot of questions there. So I'll start with the first one, which is the scarcity thing. That's definitely a thing where deposits that were easy to find near the surface that had a lot of these different minerals and metals, they're harder and harder to find. But what we have improved upon is the ability to remove the metals from the rock. We're doing that more environmentally sound ways, and we're doing that to a much greater degree of efficiency. So that has helped to correlate and to help to make up for the fact we're not finding some of these big deposits. But I'll have you recall the Grasberg deposit I showed. That wasn't discovered until 1988. And that's the world's richest copper gold mine. Together, both metals, copper, gold, and silver. Those three, it is the richest in the world, and it was discovered by one geologist who was dropped off on top of a mountain by a helicopter because there's no roads there, and was exploring around and happened to find that deposit. So this is where I'm an optimist and say, well, if we continue to work, we can find these. And we know that the stuff is in the crust. We just have to be able to find it. And you're right, though. Will finding new deposits get relatively more expensive? Yeah. The price of labor goes up. The amount of cost for analytical services, for characterizing these, this is all going to go up. And so hope if it gets to the point where it's too expensive, then that's when we'll have to switch to something else. And so the final question is China's attempt to capture ownership of the rare earth materials. This gets into a little bit of geopolitical, which I'm going to try to avoid as much as I can. But what China did, just on the face of it, is they were selling rare earth elements in the 90s, beginning in the late 90s and early 2000s, at a cost that was below how much it cost them to produce. So they were selling those at a loss. And the reason they did that, I'll suppose that, because I can't say that, because I'm not in the Chinese government, but I'll say that the reason I think they did that is because if you drive the other mining companies out of business, and there's only a couple that were doing rare earth elements, then everybody has to come to you. And that's exactly what happened. The Mountain Pass mine closed. That was the major producer in the world until the mid-90s. It was the major mine in the world for rare earth elements. And then it had to close within 5 to 6 years because its price was undercut. And the U.S. government wasn't providing stipends or stimulants or anything for or a package for that mine. So it just lost its ability. And so then by cornering the market, they then were able to raise the price back up. The deposit in China is actually easier to process than the deposit in California at the Mountain Pass mine as well. So that's part of it as well. But I'm hopeful because I think the U.S. government and other governments recognize how important these are, not just for green energy, but for other critical infrastructure. So that's why there's been a lot of focus by the USGS and other government bodies at looking for these and trying to keep it open. So then Stephanie asked about lava traps. Lava, every rock, especially lava, is going to have these elements in them. But it's not at high enough concentrations for us to be able to process the lava enough. There are some lava-based deposits out there. There are copper-based ones. There's some nickel-based ones. But for rare earth elements, it's really that extra refinement step, which is either weathering or that carbonatite magma. That's really what's required for that to happen. So unfortunately, there's lots of metals there. We might be able to get some iron out of those and some nickel out of those, but it's the rare earth elements, not so much. All right, so then Greg responded, The World in a Grain. He read the book about the growing scarcity of sand, and that's exactly right. That's another one. I didn't talk about sand much. So pure sand, which is predominantly quartz, is very important for a lot of processes. It's important for lenses. It's important for glass. We use that sand in hydraulic fracturing operations, which is what's allowing the U.S. to produce a fair amount of oil and gas. So that sand, which only had use really for glass, in the last 10 years or so, we're using it for fiber optic cables, which I'm presenting to you by using a fiber optic cable tonight. That's how my internet works. So without that, I wouldn't be able to do this. So that type of deposit, that's just sand. That's just like sand you find on a beach. Good clean sand is being mined out at different places around the world. Now we have a lot of it, but for the high quality sand, that is getting scarce. And so this is again another point where the government it can step in, and it can do that by providing resources to people, like me and like other companies to look for these, to look for more, to be able to utilize other possibilities. And this is more of an engineering thing. So if it's not clean sand, what else could we use? There's lots of work being done in those areas. But again, it's the time issue. It's the amount of time from the original research study to bringing that to market. That seems to be slower than the economy's needing and how this works. Okay, I think I answered that question. And so then the next one is, Rob Grabowski. I remember you. He was a former student. I do remember you. Thanks for stopping in. And then Jen asked is, can we assume REs are found on other planets? And that's a great question. Yes, nucleosynthesis is responsible for the limited abundance of all of these, the copper, the iron. Iron's actually pretty abundant at 5% of the Earth, and it can be found in other places, but for things like indium, for gold, for platinum, nucleosynthesis is the way that stars make elements, and so that is the requirement to get to this point. And so that process, it's hard to make the rare earth elements, it's hard to make gold, it's hard to make silver, it's hard to make indium. And that requires a lot of, I don't want to say work per se, but it required a lot of nuclei combining together to be able to do it. That's why we don't have a lot of these. So we have lots of hydrogen, helium, lithium. We have, in our Earth, we have lots of oxygen, silicon, iron in the core, but the rare earth elements, yeah, they're a lot more difficult to find.
I had a couple of comments.
Okay.
You teach economic geology. Tell us a little bit about that.
So similar to tonight's talk, we do go into the economic side of things. That's usually in the beginning of the first part of the semester, and then after that, we go into the specific deposits and the specific minerals you'll find in there and how they form. So for that class, it's for kind of more upper level geology people. Some other non-geologists have taken it in the past, but it's more focused on preparing geologists to be able to go out into the real world and get jobs with these mining companies that are trying to explore for these types of deposits. And so the students at NIU have been remarkably successful in doing that and being able to apply that knowledge from that class and others to get these types of positions in these environments. So the class, again, focuses on things like, what do we see? What would you expect to see in the rocks? What kind of minerals? What type of environment? Is it volcanic driven? Is it not volcano? Is it something else? And then we go through how they formed and what you need to look for to find new ones. I don't know if that made sense.
And I don't know if you talked about this. I think you did mention it, but I thought it was fascinating that there are several of these elements that you talked about that we actually haven't used years ago. We never had a need for them. And now, all of a sudden, even though they were on the chart, we didn't really talk about them or use them very much. And now they are becoming very critical to our new technology and the things that we want in the real world.
Yeah, it's really amazing. And one of the ones that I've discussed is indium. Indium is an element that is sitting there between cadmium and tin. Tin we used quite a bit. And so that's one of those elements that we just didn't really use. We didn't really, there was no reason. It was at low enough concentrations. We didn't put it in the cans like we did with tin. So we just kind of like, okay, it's there. And so there's a lot of mines that were processing rocks that had some indium in it, but nobody was really doing much with it because there was no source, no reason to use it. But now we can't have touchscreens without indium. It's one of the indium oxides that goes into touchscreens. So all of a sudden now they're like, wait, we're starting to run out of indium because we didn't really look for it, we didn't really mine it, and now we're using it a lot. And so there's actually been some colleagues of mine that we've gotten grants to look for indium to try to figure out how indium behaves and where you're going to find it. There's indium deposits in Canada and some in Alaska that we don't really know how they got there. And so once we can figure that out, we can start looking other places for them. On the flip side, an element like lead is a great example of something that we had enough of and we were using. And then we found out that there are consequences to using lead. So if those of us who are old enough know that lead is used in paint in the old days because it was one of the elements that can turn paint white. And so we used lead in white paint, and we would paint our houses with this paint, white paint. And then what happened is we found out that if kids ate the paint chips, then they'd have developmental issues, and then that was a big problem. So they actually restricted lead in both gasoline and paint chips when this was found out. And so one of the only other elements that can actually turn paint white is titanium. So titanium, which is used in all types of alloys, it's actually the major use of titanium is actually to make paint white. It's pretty remarkable. So I think I got all the questions.
Well, we're giving people a couple of minutes to either think about whether they have any more comments. I do want to tell you about our next virtual STEM Cafe, which is going to be October 21st, and the topic is the fear of first contact, how science and fiction inform our search for alien life. Our speakers will be authors Daniel Kraus and Patrick Tomlinson, and physicist Dr. Clarence Chang. So that will be on the 21st. And of course, we have one the last week of October too. All of this as part of STEMFest. And the one on the 28th will be the science behind haunted houses. So we'll have some fun with that. I also failed to mention that on October 31st is going to be our big bash. You know, we used to have it in the Convocation Center, but October 31st is going to be as close as we can get to what we had in the Convocation Center. We're going to have 4 different virtual rooms with a variety of choices in each one. And so you can see what we have planned on the schedule if you go to NIU STEAM site or put in the search STEMFest. And you should find out all the things that we're going to be doing. We're going to have a celebration stage, and we're going to have some live demonstrations, semi-live, I should say, and then 4 virtual rooms. And again, 12 other activities at least for the rest of the month, or for the total month. And were there any other questions or comments? I want to again thank you, Dr. Frank, for having had this presentation for us today. It was a pleasure to have you with us this evening. And if it's all right with you, I could find out a way to put your PowerPoint in there. We are going to have this, you can refer back to this presentation because within about a week to week and a half, we are going to have it stored. Somebody asked, where is it going to be stored? If you pull up STEM Cafes on our website, you will go to my STEM Cafe site, and then on there you will see that there are the upcoming events, the recorded events, and past events. So it will be there under recorded. But again, we have to get the closed captions done. And let me see, am I missing anything else? Yes, and again, thank you to our sponsors. If anyone is interested in sponsoring a STEM Cafe or any of our programs, if you could go to niu.edu, give NIU STEAM, which I have on the screen here, and go into donate. You can find the designation STEM Outreach, and or just go into NIU STEAM and find the spot for donate. It would really be great if you did, anybody that is interested, because we are providing these programs for the community, and all of our STEM cafes have been free of charge. If you do have a particular topic and you would like to sponsor a particular event, we can also do that. I think we did that once before, so that is also an opportunity. So email me if you have any suggestions or feedback on our STEMFest Cafe tonight. Again, thank you to our sponsors, Ideal Industries, ComEd, 3M, Nicor Gas, Thermo Fisher, First National Bank of Omaha, and Mortenson Company. Thank you to Aline Click, our NIU Director of Web Media and E-Learning, and her staff, Roz Aldul Sarani and Rebecca Griffith, who were behind the scenes tonight helping us out with our platform. So thank you very much to those persons. And thank you, audience, for joining us. I hope that you will join us again. Please do send me your feedback. We really do appreciate any of your suggestions for STEM cafes. In fact, one of our members in the audience recommended this particular STEM cafe, and one that is going to be coming up in the next few months. And we have our STEM cafes almost planned through April and May. We definitely have the next 2 ready to go, and next 3 ready to go. So we really appreciate any feedback you can give us. I hope that you enjoy STEMFest, and thank you for joining us. And again, thank you, Dr. Mark Frank.
Thank you.
Did we miss anything on any comments here?